All right, so we're going to start by kind of summarizing what we did last class period when we started talking about reactions of ethers. Right, we introduced this chapter talking about nomenclature, and then we started talking about reactions of ethers. All right, and we had a few ways, a few reactions. One way to make it, our acid catalyzed ether synthesis. All right, so just to review, everybody take a second and give me the product here of our acid catalyzed ether synthesis reaction. Remember, we catalyzed this with our strong acid sulfuric acid. And then we learned a way that we could break it up. So our acidic cleavage of ethers. Right, now we're starting with our ether reactant. And we're cleaving it with that hydrohalic acid. We're going to do hydroiodic acid. And everybody's going to take a second and complete these chemical equations for me. All right, for our acid catalyzed ether synthesis here, this was a way in which we could make symmetric ethers. We took our alcohol, and under these acidic conditions, one of them will get protonated and play the role of the electrophile in the reaction. The other one will remain neutral and play the role of the nucleophile. So we end up joining these two fragments together to create a symmetric ether. All right, we said we had two equivalents of alcohol reacting with one another to create our symmetric ether. When we did our acid cleavage, acidic cleavage of ethers, we get these two products, right? Because now we're chopping our ether in half. One of them will be an alcohol, and the other an alkyl halide. All right, we're going to protonate that ether, and then that halide ion is going to play the role of a nucleophile. Break this thing apart. It's got to attack one of these carbons here. If I look, that blue carbon has one carbon neighbor, or is a primary carbon. My red carbon has 0 carbon neighbors, or is a methyl carbon. And which one is more likely to get attacked by that nucleophile? Primary or methyl? It's going to be the methyl, and why was that? Easier access, right? More accessible, and that's going to be the theme of the day, all right? We're going to talk a lot of mechanisms today, and the theme of the day is going to be nucleophiles attack the more accessible carbon. So that means that that more accessible fragment is going to have my halide ion, or now I guess my halogen, and that less accessible fragment will be my alcohol. It's too big. Okay, and just to note, these are two reactions that we covered thus far, and they're both reactions that we have reaction mechanisms for. Okay, so just note, we should know not only how to do our substrate reagent product combinations for these, but we should also know our mechanisms for these reactions. And now we're going to add one more to this list here, what's called a Williamson ether synthesis. All right, and what we're going to find is this Williamson ether synthesis is a great way to create an asymmetric ether. Okay, when we were talking about creating our symmetric ether, we were talking about, oh, how do we make that hydroxyl group into a good leaving group? Well, one method is to protonate it, right? So we can just accomplish that simply by adding in some acid, a nice cheap way to do it. And then there was a more complicated way to do it, which is turning it into an alkyl halide, what somebody said. And that's exactly what we're going to take advantage of here in our Williamson ether synthesis. We're going to do a reaction between an alcohol and an alkyl halide. All right, we're going to join these two pieces together here. So just to kind of keep track of what's what, I got my 3-carbon alcohol is going to join with my 2-carbon alkyl halide to create my ether. Okay, now these two will not react just by themselves. We're going to have to do a first step. That's actually the second step. The first step is to treat this with what's called sodium hydride, NaH. All right, and this is yet another one that we're going to learn our reaction mechanism for. So let's take this exact example and kind of detail it step by step here. Okay, so we're going to look at this first step with our sodium hydride. And when we see sodium, we're going to get in the habit of doing what? Getting rid of it. And not just going to get rid of it, we got to replace it with something. Right, that sodium ion has a charge of +1, which means that this thing has to have a charge of -1. So we're going to replace it with that lone pair and that minus sign here. Okay, this is what's called a hydride ion. And this thing is a super strong base. Not like your general chemistry sodium hydroxide strong base, like much stronger than that next level up. All right? And that's going to be important because our goal here is going to be to deprotonate this alcohol here. And alcohols are not good acids. They're pretty hard to remove a proton from an alcohol. We can't use sodium hydroxide to remove a proton from an alcohol, for example. So we have to use a next level up, stronger base than that. And that's exactly what these hydride ions do very well. They deprotonate our alcohols. All right, so to show my mechanism, I actually have to be good and show my oxygen-hydrogen bond here. And everybody's going to take a second and put in electron pushing arrows to deprotonate that alcohol. What the heck do I mean by deprotonate that alcohol? Everybody show me using those electron pushing arrows. So by deprotonate, I mean that hydrogen's going to grab that other hydrogen and that pair of electrons jump onto that oxygen. Let me take a second. Let's look at our organic intermediate here. When that bond breaks, that pair of bonding electrons becomes a lone pair on my oxygen. All right. These things here, these negatively charged oxygens with this alkyl tail here, these are called alkoxide ions. Right? Hydroxide would be hydrogen in that negatively charged oxygen. Alk oxide because I have an alkyl chain and an oxide ion. These alkoxide ions are strong bases, but importantly for this reaction, they're also strong nucleophiles. Okay, but let's take a second and look at our inorganic product here. All right, we said that this was a simple bond breaking arrow. What about this arrow here? What did that do? Bond formation, bond breaking, both. This would be a formation arrow. So I formed a new bond between what? Hydrogen and hydrogen, which means that my product here is that my inorganic product is H2. And what do we know about H2? Hydrogen, solid, liquid, gas. It's a gas, right? So what happens is you create this gaseous hydrogen atom, our molecule, that then just bubbles out of your solution. So this is a really efficient way of creating these alkoxide ions because I have absolutely no chance of this going back in the reverse direction, right? My hydrogen has left the building. It's gone. It's out in the room now. All right? So we've created now a beaker full of our good nucleophiles, alkoxide ions, which is where we go with that next step of our reaction. We follow that up with our alkyl halide. All right, and what do we know about alkyl halides? Yeah, we got a good electrophile because we have this good leaving group here. So these things are good electrophiles. Why are they good electrophiles? Well, remember, electrophiles are what? Electron rich or electron poor? Electron poor. We have this carbon-bromine bond here. What's more electronegative, bromine or carbon?
Bromine.
Yeah, bromine. So that means my bromine's got a bunch of electron density. My carbon's left relatively electron poor. So check, check. All right. The other important thing about an electrophile is it has to actually be able to accept a pair of electrons. The reason why this can accept a pair of electrons is because I'm not going to stop there. That would violate carbon's octet rule. But because I have this good leaving group on there, that bromide ion. Right, so that bromide ion that gets kicked off is a good leaving group? Right? What makes it a good leaving group is that it's nice and stable all by itself. Another way of saying that was that it is a weak base. And so that's how I connect these two fragments together, forming my asymmetric ether. All right, so here's our Williamson ether synthesis reaction mechanism. We're going to do this again, but we're going to look at a little bit more complicated of an ether here. So now our goal is to take some alcohol and some alkyl halide. We're going to have to first treat that alcohol with our sodium hydride. Then we can treat it with that alkyl halide, and we're trying to create this particular ether. All right, but if we look, we're kind of just gluing these two ends together, our alcohol fragment and our alkyl halide fragment. That's what's going to make up our ether here. So the question is, which one's which, right? So I'm going to color this left side in orange, and I'm going to color the other side in green. All right, and so the question is, which half is my alkyl halide and which half is my alcohol? So let's compare these two. All right, we got two possibilities. On the one, I'm going to make my alcohol that green fragment. Which means that my alkyl halide would be that orange fragment. And on my other one, I'm going to do the reverse. I'm going to instead make the orange fragment my alcohol. And I'm going to make the green fragment my alkyl halide. All right, now in terms of our pencil and paper organic chemistry, either of these work, but practically speaking, one's going to be way more efficient in the lab than the other one. All right, one of these methods is way more preferable than the other one. In order to see which one's which, let's take a look at our alkoxide intermediate. So I'm going to deprotonate that alcohol. Same thing over here. I'm going to deprotonate my alcohol. Okay, and then I want everybody to take that intermediate and put in those electron pushing arrows that'll take us to our product side here. So starting out with this alkoxide ion and this alkyl halide, put in our electron pushing arrows. Same thing down here, put in our electron pushing arrows, and we're going to compare and see which one's more favorable. So everybody take a second and fill in our missing electron pushing arrows to take us to our product side. so that nucleophile is going to attack that partially positive carbon, kicking off that leaving group. I'm going to have the same thing down here. My nucleophile attacks that partially positive carbon, kicking off that leaving group. And again, in terms of our like pencil and paper, putting in these arrows here, I didn't do anything illegal when I put in my mechanism arrows. But nonetheless, one of these pathways is way more favorable than the other one. So let's look carefully. What do we think? We're going to use the top combination or the bottom combination? Which one's going to be better? Why the bottom? The more accessible, the nucleophile is going to attack that more accessible carbon. Look at where that nucleophile is going to have to get to in order to attack this carbon. It's being blocked by all these other methyl groups in there, right? Preventing it from being able to get to that carbon. Whereas this nice and accessible methyl carbon here is going to be very easily attacked. So again, theme of the day. Okay, our nucleophile is going to attack. Nucleophiles attack more accessible carbons. All right, that key word again being accessibility. All right, so these are our three reactions of ethers, and that's all we got for ethers. Like I said, kind of a boring functional group here. Not very good starting point for any sort of organic synthesis. We got two ways to make them, one way to break them apart. That's about it, all right? But to illustrate this, specificity of this Williamson ether synthesis, everybody's going to take a second. Let's use this particular example. Just put it in here so we can really see the differences here. And you're going to tell me what alkyl halide and what alcohol I need in order to create this product here. All right, again, that nucleophile wants to attack that more accessible carbon, so that more accessible carbon needs to be my electrophile, my alkyl halide. And my nucleophile, that alcohol, or will be alkoxide ion, is going to be on that less accessible fragment. Cool. So again, our reactions of ethers, we got two ways to make them and one way that we can break it apart. All right, so for the rest of the class period and actually the rest of the week, we're going to talk about a very special ether, so special that we give it its own functional group category, what's called an epoxide. All right, so an epoxide is an ether. We have an oxygen sandwiched between two carbons. But importantly, it's been kinked into this three-membered ring here. So that's this essential feature of an epoxide. An epoxide is a three-membered carbon-oxygen-carbon ring. All right, there may be some other carbons coming off here. This would still be an epoxide, but importantly, we have to have that three-membered ring in order to be an epoxide. All right. And based on what we discussed the very first semester when we were talking about cyclic alkanes, what do we know about three-membered rings? Are they nice and stable or unstable? They're unstable. So three-membered rings are very unstable. All right. In fact, if we look, we can compare the stability of rings as a function of ring size. Our three-membered rings are the least stable, the highest energy of all of our rings that we can have, right? The most stable being those six-membered rings. Five-membered rings are pretty good, but those three-membered rings are absolutely the least stable. So why is that? All right. So first of all, let's make a triangle. And if we assume this is an equilateral triangle so that all of our bond angles are equal, they all got to sum to 180. So what's going to be the angle of each of these bonds here? 60 degrees. But this sp3 hybridized carbon wants to have a bond angle of what? Does anybody remember the magic number for a tetrahedral carbon? 109.5. 120 was for trigonal planar, but close enough. Anyways, much bigger than 60 degrees, right? So this creates what's called angle strain. The fact that we had to take this carbon and bend that bond into a far more acute bond angle than it wants to have. Not only that, but the only way that we can make a triangle is if all those atoms lie in the same plane, which means that all of those bonds are going to be perfectly parallel to one another, or what we call the eclipsed conformation. And bonds like to be as far apart as possible, right? Electron groups don't like sitting directly next to one another. They want to instead have what's called this staggered conformation. That's what cyclohexane has that makes it so stable, where every other bond is perfectly sitting between the other ones. So our cyclopropane rings, any three-membered rings, they have these eclipsed bond angles here, all right? So our three-membered rings are super unstable. All right, and that's because they have what's called angle strain due to that acute bond angle. As well as what's called torsional strain due to those eclipsed bonds. All right, so all that to say, our epoxides here are very unstable, which means that they are very reactive. So unlike ethers that we said were super boring, epoxides, as soon as we kink that ether into a three-membered ring, all of a sudden we've raised its energy a ton, and it wants to react in order to relieve that angle and ring strain, our angle and torsional strain. All right, so these epoxides are going to undergo what are called nucleophilic ring opening reactions. All right, where we're going to take our epoxide, we're going to treat it with some nucleophile. All right, we're going to also see that there's going to be some proton source in our reaction mixture as well. And what happens is we're going to break our ring. We're going to open it up, right? So it's kinked into this three-membered ring. These reactions will open that ring up. So to be clear, I'm going to color these carbons so we can keep track of who's who. If I break that bond that I've marked here in red, then importantly that orange oxygen still has that, that orange carbon still has that oxygen bonded to it. Because that proton source, it will become an OH group or an alcohol. And the other carbon now has that nucleophile attached. All right, so these are these nucleophilic ring opening reactions. The real thing that you should have tied in your mind to the reactions of epoxides is that phrase ring opening, right? That's this common thread that we're going to see, is it breaks that bond, that carbon-oxygen bond in our epoxide. All right, and so why are we going to use a nucleophile to do it? Well, as a reminder here, we have this polar carbon-oxygen bond, right? Oxygen's much more electronegative than carbon. So oxygen's got a bunch of electron density. Carbon's left relatively electron deficient. Typically we don't see, so for example in alcohols, we don't see that same sort of nucleophilic substitution because as we said, this is not a great leaving group. But because of the instability in this ring, it's going to be more than happy to accept that pair of electrons. All right, so because we have this three-membered ring, we're going to have a nucleophile attack that carbon in my epoxide. All right, so let's look at a particular reaction here. Our nucleophilic ring opening reactions. And we're going to see that this will occur under both acidic and basic conditions, and we're going to discuss them separately. So the first one we're going to do is talk about our basic conditions here. Under basic conditions, remember we should have no strong acids. Right? Which means that we should not see any positively charged intermediates. Which is cool because if we're trying to use our nucleophiles here, do our good nucleophiles have positive charges in the first place? No, our strong nucleophiles are negatively charged, right? So under basic conditions, we get to use our strong nucleophiles with their negative charge. Okay, so let's take a look at an example. We're going to grab our three-membered ring here. I'm going to use this nitrogen nucleophile. And I get to use my strong nitrogen nucleophile with its negative charge. Nitrogen would have two lone pairs and two bonds to have that negative charge. All right, and I'm going to start out with this symmetric epoxide here, meaning it doesn't matter which carbon I attack. I'm still going to kind of keep track of who's who so we can see this ring opening a little bit more clearly by coloring one in orange and one in green. But we're going to have our nucleophilic attack followed by that ring opening, right? So our leaving group, this pair of electrons here, jumping up onto that oxygen. So everybody's going to take a second and draw me my intermediate in this reaction. All right, so my rings open. Based on the way that I drew my arrows here, my orange carbon retains that oxygen, whereas my green carbon now has that nitrogen, that nucleophile attached. This pair of electrons that was in my carbon-oxygen bond, when my ring opening happened, it jumped onto that oxygen, creating that alkoxide ion. All right, now like I said, in this reaction mixture, we're going to have some source of proton as well, which means that my product here will have that oxygen eventually protonated. All right, but what am I going to use here in order to do it? Remember, we can't have any strong acids in our mixture, but we need a proton source. We need an acid. So what am I going to use?
Water.
All right, water is a great guess. But there's going to be a problem if I use water in this particular reaction mixture. Water is a great guess because it is a weak acid. It would totally do the job of being a proton donor. The problem is if I have this molecule, especially this molecule in particular, in my reaction mixture with water, it's an even better base than water is, or than hydroxide is. So this reaction would proceed and I'd create an amine and a hydroxide ion. I'd effectively destroy my nucleophile if I had water in my reaction mixture. All right, so I couldn't put water in there and still have this reaction go forward. So what we're going to do is we're going to be really clever, and instead of using water, we're going to use the protonated form of whatever our nucleophile is. So my acid that I'm going to use here is whatever my nucleophile is plus an extra proton. All right, so what do I mean by that? I'm going to take my nucleophile. Instead of having it be its strong nucleophile version with that negative charge, I'm going to have it be its neutral version, adding an extra proton on there. All right, so in this case here, it would be this. All right, I'll even draw it the exact same so we can see clearly. Now it's got this extra hydrogen on there. Now you might be thinking, well, doesn't this do just the exact same thing as what we said before? This thing's going to instead react with its neutral version here. But why isn't this a problem? Because I get the exact same thing. So this reaction absolutely will happen. Nucleophile reacting with your protonated nucleophile. But at the end, what I'm going to create is the exact same thing that I started with. All right, so sure, I've exchanged a proton from one nitrogen to the other, but I haven't actually depleted my stock of nucleophile in my reaction mixture. All right, so with these reactions, and what often happens is you're clever about your source of proton. You make sure to use your protonated form of your nucleophile. Okay, so then just to finish this off, everybody take a second and complete our reaction mechanism using that amine. We'll be good and show that nitrogen-hydrogen bond explicitly. Boom. And this even has the added benefit of I've replenished my stock of nucleophile here. All right, cool. So we're going to play this same game here. But now we're going to make things a little bit more complicated. We've been doing things just with our very simplest epoxide, 2 carbons, 1 oxygen. Now we're going to add a few more carbons onto our epoxide here. Oops. We're going to treat it with some nucleophile. I'm going to use a methoxide ion here, a 1 carbon alkoxide. Which means that what solvent am I going to want to use? I'm going to take my nucleophile and do what to it? Protonate it. Cool. So I'm going to replace one of those lone pairs with a hydrogen, leaving us with methanol. All right, so here's my reaction mixture that I'm going to use. Okay, but the question is, where does my nucleophile actually attack? It can attack this green carbon, leading to my ring opening reaction. Importantly, that would, let me just color these blue and red, make it easier. Yeah, totally where we're going here. All right, but let's just sort of convince ourselves that we would get a different product if our nucleophile attacks the blue carbon. Right, now my methoxide ion would be attached to the blue carbon, which means that the red carbon would maintain that OH. Or if instead it attacked that red carbon, I'd have my ring opening in the other direction. Right, which means that that blue carbon retains that epoxide oxygen forming that OH. Okay, so first of all, let's convince ourselves that because we started out with this asymmetric epoxide, now we're going to get a different product depending on where that nucleophile attacks. Nucleophile attacks the blue carbon, it'll be attached to the blue carbon, and that epoxide oxygen will be on the red carbon. Or if it attacks the red oxygen, the red carbon, my nucleophile is attached to the red carbon and my epoxide oxygen on the blue carbon. And one of these two paths is more preferable than the other. And somebody already said it. What was the word of the day? Accessibility, right? So which one of these carbons is my nucleophile going to attack, red or blue? Red, because red is more accessible. Right, so I will get this product specifically All right, because as we've been saying all day here, our nucleophile attacks that more accessible carbon. All right, so this is what we would call our epoxide ring opening regiospecificity. And under those basic conditions, our nucleophile will attack that more accessible carbon. So primary carbons, I guess actually methyl carbons, can't be methyl. Gotta be primary carbons are more accessible than secondary carbons, are more accessible than tertiary carbons. All right, so where does our nucleophile attack? All right, primary carbons will be more preferable than secondary carbons, will be more preferable than tertiary carbons because, again, of that accessibility argument. Cool. We're going to stop here. Like I said, epoxides also react under acidic conditions. And don't worry, we'll complicate things next time talking about that. Yeah, so you...
So this is going to open up, it's going to come
Yeah,
down.
so look though, this is the fragment that has that that oxygen on there. So you drew the product as if it attacked over here, right? Your nucleophile oxygen, this has to have the carbon on
yeah.
it. This one doesn't have the carbon on
This,
it.
right?
Yeah,
So it'd be,
that there, and then this one then doesn't have the carbon on it. That's your epoxide
which
oxygen.
then gets protonated?
Yeah, that's the one that will end up having to do the protonation step down here. Yep. So since this was negatively charged, when it forms a new bond, it's neutral. This one, when it accepts a pair of electrons, this one will be negatively charged.
Oh, I see. So this guy swings down like that.
Yeah, it kind of like, yeah, we'd actually, and we'll talk about this next class period. Really, what you want to do is draw your arrow going the other direction. It'll always attack from the back side.
Oh, okay.
So it goes over here. So this one's pointed up and this one's pointed down. It's not really a big deal for this particular example, but we'll see examples where it does matter.
All right, thanks, Doc.
Yep.